So let's talk about imaginary numbers first. Recall that imaginary numbers were created so that we could deal with these types of equations where we have square roots of negatives. So, for example, we define the imaginary unit as I, which is the square root of -1. Now, why that's useful is if I have the square root of, say, -8, for example, I could rethink of -8 as basically -1 times 4 times 2, and I can have a method of reducing this or simplifying it. The square root of 4 is 2, the square root of -1 is I, and then I'm left with a square root of 2 still in that expression. So I can reduce now values that have square root of negative numbers. As a result of this definition too, we can look at higher powers of I, such as I squared would be the square root of -1 squared, or -1. I to the third would be -1, would be I squared times I, both of which we already know. I squared is -1, so this will be -1 times I, which is the square root of -1, so just negative I basically. I to the fourth we can think of as I squared times I squared. Well, I squared is -1, so this is -1 times -1, which is +1. And I could do this for pretty much any power of I. If I think back to these four basic ones, say I to the 7th would be I to the 4th times I cubed. Well, I to the 4th is just 1, we saw before, and then I'm left with I cubed, which is -I. So this would simplify to simply -I. So we can use that for simplifying higher powers of I, but I itself is, again, back to just a radical. So rationalizing comes to mind when we have to deal with this. Looking at the first example, if I want to rationalize something, just like we don't leave radicals in denominators, and I is just a special type of radical, we don't want i's in denominators either. So we have to rationalize this, much like we did with radicals, by multiplying by its conjugate, which would be 3 minus 2i, under 3 minus 2i, and then distribute everything. My denominator will reduce to 9 minus 4i squared. And recall that I squared is just -1, so I can actually rewrite that whole denominator as 9 plus 4. Sorry, little glitch. There we go. 9 plus 4, which is 13. So let me rewrite that. Let me erase some of the stuff, get it out of my way. Here we go. Use a black color. So my denominator we saw would be 9 plus 4, which was 13. My numerator, when I distribute, will be -1 times 3, which is -3. -1 times -2i, which would be plus 2i. -I times positive 3 would be -3i, and -I times -2i would be plus 2i squared. So this whole numerator becomes, well, I squared is -1, so it'll be -3 minus 2, which is -5. 2 minus 3i will be minus I, all divided by 13. It's a simplified expression involving i's. Now, when we multiply i's, such as, or we multiply negative exponents, before, this is very important, before we multiply the values in the exponents, we first must convert to this imaginary unit, because this is how we're going to define negative radicals. Without this imaginary unit, they are meaningless. So I'm going to rewrite this as I square root of 6 when I factor out that -1 times I square root of 3, which gives me I squared square root of 18. There's a factor of 9 in here, so that will give me 3 times I squared, which is -1, so that would be -3 square root, and that was the 9 that I pulled out, which is what gave me the 3, so it leaves me with the 2 in the radical. If you don't first convert to this imaginary unit, you're going to lose your sign and lose that negative, and result in getting the question wrong. Finally, we have some powers of I. So here I have I to the 5th. I can break this as I to the fourth, which is 1, times I, so this I to the fifth will reduce to just I, minus, well, the square root of 4 is 2, and the square root of negative 1 is I, plus 5I, so I end up with 6I minus 2I, which would be 4I altogether. Okay. Now we looked at this imaginary unit because it was a result of some quadratic equations that were initially unsolvable because they had no real solutions, but now we have this imaginary number to represent solutions. Solving quadratic equations, there's a series of examples that we went through. This is basically an overview of how to decide which method that we would use. How to read through it is from the starting position I would ask myself the question, can I quickly isolate a perfect square? If so, then I would solve by simply square rooting each side and resulting in my final answer. If I cannot quickly isolate a perfect square, I'm going to move down to ask myself, is the equation factorable? If it is, I'd solve it by factoring, by any of the multiple factoring methods that we talked about in the preliminary section of the preliminaries video. If it's not factorable, I'm going to see if my coefficient of my quadratic term, that's that coefficient in front of the x squared value, is 1. If it is, and it wasn't factorable, I'm going to solve by completing the square. Once I've completed the square, I'm going to continue by taking square roots. If the coefficient's not 1, then the quickest method is going to be just using the quadratic formula. So let's apply that into these 3 examples. Looking now at the first one, it does not seem like I can quickly isolate a perfect square. If you're wondering what isolating a perfect square would look like, that's actually the second example. Notice that 2x squared is a perfect square, so I could go ahead and take square roots of both sides. So why don't we go ahead and do that one first. Since 4x squared is a perfect square, if I take square roots of both sides, remember when I take square roots I have to account for the plus and the minus solutions, both positive and negative. The square root of 4x squared is 2x. The square root of 20, there's a perfect square of 4, so that'll be 2 square root of 5, and there is a positive and a negative solution for that. Then if I want x, I simply divide both sides by 2, and I get x equals plus or minus 2 rad 5 over 2, which is just square root of 5. So that's an example of where you would just go ahead and take square roots, because I could quickly isolate that perfect square. In the first example, that's not possible, so I'm going to see if I can do it by factoring. So I'm going to look at the sum and product of this example. Be a sum of positive 1 and a product of 2 times 3, which would be negative 6. Two numbers do add and multiply to that would be positive 3 and negative 2. So I'm going to split my middle term into 3x minus 2x. I'm going to bring down my other 2 terms, so it'll be 2x squared plus this, and then minus 3, all equal to 0. Don't forget that other side of your equation. Then I will factor by grouping, so I can factor this as a common factor of x. When I take out that factor of x, I'm left with 2x plus 3. My second group has a common factor of negative 1, and I'm left with 2x plus 3, all equals 0. And now I have 2x plus 3 times x minus 1 equals 0, so that either x equals negative 3 halves or x equals 1. So I get my 2 solutions from that by solving by factoring. For the last one, there is no numbers that will multiply to 13 and add to negative 6. In fact, the only factors of 13 are 1 and 13. Which don't add to negative 6. So I'm going to check my leading coefficient. So that value in front of the x squared, which is in fact 1. So I'm going to solve this by completing the square. Now to do completing the square, which is usually the method that most students overlook and is actually one of the most convenient for avoiding mistakes in quadratic formula, I'm going to isolate all the variables to one side and get my number, my constant, to the other. Then, to complete this square, I need to take half of this value, which is negative 3, and square it, which is positive 9. So I'm adding 9 to my left-hand side. I must also do the same to the right-hand side in order for this equation to stay equal. And I end up with a perfect square on the left, which factors to x minus 3 squared, equal to negative 13 plus 9 will give me negative 4. Since I have a perfect square on the left-hand side, I can solve this by taking square roots. So I'm going to take the square root of both sides, and when I take square roots, I get a plus and a minus. So the square root of this will be x minus 3 equals plus or minus, I have a negative, which means I'm going to have an imaginary solution. Well, the square root of 4 is 2, and the square root of negative 1 is I. So I do have a solution. It's an imaginary solution. Now I'll add 3 to both sides to get my value for x, and it's 3 plus or minus 2i. So I have 2 imaginary solutions in this case. Now, that was solving for the roots or the solutions to this quadratic equation. Now, just as we can solve for the roots going through the equation in this process, we can do this process in reverse. Notice that in this factoring method that the roots showed up as the minus factors for these. So if I know what 2 of the roots are for a quadratic equation, those are basically the 2 solutions. X equals negative 3 and x equals 2 are my 2 solutions for this quadratic equation. That means that x plus 3 equals 0 would be a factor, and x minus 2 equals 0 would be a factor. So that's basically doing this solving process in reverse to make the quadratic equation from the given roots. Well, if x plus 3 is a factor and x minus 2 is a factor, this is what my quadratic equation would look like. Then if I FOIL, I end up with x squared plus x minus 6 equals 0. So there's a quadratic equation that would have negative 3 and positive 2 as its roots. Okay. Now sometimes we want to figure out just what the solutions to a quadratic equation would look like without actually going through this whole solving process. So that's determining the number and nature of the roots. The number of the roots is how many solutions we have. The nature is whether or not they are real numbers or irrational or imaginary numbers. So let's take a look. In order to determine that, we're going to use the discriminant, which is b squared minus 4ac. So how we interpret this discriminant is in the following way. If the discriminant is a positive number that's greater than 0, I'll have 2, which is the number of solutions, and those solutions will be real numbers, meaning that they have no i's or imaginary numbers in them. If the discriminant is equal to 0, there is exactly 1 real root or real solution, and if the discriminant is less than 0, in geometry last year we said that there was no real solutions, but now this year that we've talked about imaginary numbers, it turns out that there are 2 imaginary roots, or 2 imaginary solutions. So let's see how we would do that in this example. Well, in order to read off the discriminant, I need to first get this into standard form. So I'm going to turn on my pen, and I'm going to get this into standard form, which is having bringing all my variables to one side. So 0 equals 5x squared minus 4x plus 9. So now I can read off each of my coefficients. A is the one in front of the x squared, b is in front of the x, and c is the constant term. So b squared would be negative 4 squared, which is 16, minus 4 times a, which is 5, times c, which is 9. 4 times 5, or yeah, 4 times 5 is 20, 20 times 9 is 180, so this is 16 minus 180, which is clearly a number which is going to be negative, which is less than 0, which means I have 2 imaginary or 2 complex solutions or roots. Since the discriminant turns out to be negative, I have 2 imaginary roots.